Okay, so this is another interesting thing that I would like to discuss. So here we're looking at the just the square root function of z, and as you can see here, the branch cut of the function is now placed at the origin in the z-plane. But you can see that the z-plane is fully colored, whereas the f-plane is not, and this is just because, as we discussed, we have this function that takes the square root function takes the argument, which is some radius times e to the I some angle, and it halves the angle, but it takes the square root of the radius. So this means that in the f-plane the radius is shrunk, but this is not shown by the coloring, whereas the angle itself is halved. So 2 pi, which would be this red region here, would map to 2 pi over 2, which is 1 pi. Okay, as we discussed, we can place the branch cut location anywhere, right? So for example, here I'm placing the branch cut at 45 degrees. So what does that actually mean? So it basically means that in the square root plane, I am looking at angles of z that span pi over 2, which is this blue region, all the way to 5 pi, sorry, not, all the way to, well, this is 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. So I was right, 5 pi over 2. So from pi over 2 to 5 pi over 2. And as you can see, well, 5 pi over 2 divided by 2, that becomes 5 pi over 4, which lands around here. So that's why the square root function now represents this 45-degree line, but it also maps to a half plane. Okay, so that's quite interesting, and you can just keep going around as we discussed. But the square root function, or the power functions, if they have a fractional power, they will map to whatever is this fraction in the plane. So for example, if I have, instead of a power of 1/2, I have a power of 1/3, then I get this 1/3 of the plane, or 120 degrees of the plane is mapped. And as you can see here, the full z-plane now corresponds to a much smaller region in the color space. And of course we can just keep going around the plane and exploring it. The interesting thing is that if we make the argument of this now cube root function, we make it, let's say for example, z cubed minus 1, which is basically has 3 roots, then we get 3 branch points. So that each point corresponds to a root of this z cubed minus 1, and each one of these cuts or discontinuities represents where these two lines land on this plane. You see, both the solid white line and the dashed white line land on the same position in the plane. And again, as we go around, we move the position of the branch cut, and they do this very interesting pattern. So for example, if I'm around 60 degrees, then I get this swapping of the curves to this point, and then of course as I go around, I get another cut that is straight, even though the angle is different. And then if I keep going around, I get another of this cycle, and then I keep going around and I get the second cycle until we end up at the same position. So that's a very interesting behavior. And of course the fractional power doesn't need to be a rational number. It could be some irrational number. Let's say for example pi. Oops, not pi, 1 over pi. Pi of course is positive. So let's say for example 1 over pi, and then we get this similar mapping, but now the angle here, instead of being 2 pi over 3, it's actually 2 pi over pi, which is 2, right? So this means this is a 2 radian span. So but let's actually go back to that, because that's a very interesting point. So let's say for example we went back here and just used the z cubed, right? And we get this beautiful picture, right? And there's basically means, let's actually start with z squared, because I think it's a little bit easier to understand. So now the first thing you observe is that the branch cut line both lines lie at the same line, right? So basically, the solid and the dashed line are lying on top of each other, which means that it doesn't really matter where you place the branch cut, it doesn't do anything. And this just means that the function is not multi-valued. So on the left hand side, you can see that the function now maps to two copies of this plane. So we span, if we start here at this cyan color and we go all around the circle, on this we go all around the circle, we end up at cyan, which now ends up over here. So it's like cyan, blue, um, um, purple, red, yellow, green, and then the cyan again. And then we can go one more cycle, which just means that this squaring function doubles the angle, so we get two cycles. If we keep on increasing the exponent, we keep on increasing the number of cycles we get. So for example, if we do z to the fifth, we get this interesting five cycles of color, and it's kind of psychedelic in a sense. Yeah, and of course we can have a polynomial inside, like for example z squared minus 1, and in that case we still get this multicolored thing, but now because we have two zeros, we have 2 points where this the zeros of this polynomial basically become centers of rotation for the colorful mapping. And of course we can have more roots. For example, z to the fifth, we get 5 roots, so we have 5 points, and each point maps to a different colorful little thing. And yeah, so these are, I think, the interesting things that we can do with this. Of course, this is more of a visual thing. The reason why I built this app is to show the branch cuts of some function, let's say to the 1/3 or something like that. And then, of course, we get this very interesting behavior that we already discussed.